All right, let's talk about something that every web developer has run into, and honestly, every single person who uses the internet relies on probably without even knowing it. We're going to be demystifying cross-origin resource sharing, or CORS. It's basically the set of rules that lets the web share things without catching on fire.
If you've ever tried to build something for the web, I bet you know this feeling. That pit in your stomach when you open up the developer console and you see it. That cross-origin error. It feels like a bug, right? Like you did something wrong. But what if I told you it's not a bug at all? In fact, it's one of the most important security features of the entire web.
Yeah, that one. Cross-origin request blocked. I promise, your browser isn't trying to make your life difficult. It's actually being a really good security guard, and it's enforcing a super fundamental web policy. To get why it's blocking that request, we have to first understand the security wall that it's designed to protect.
Okay, so imagine every website you visit is its own little walled fortress. By default, the rules of the internet say that code inside one fortress is absolutely forbidden from messing with stuff in another fortress. This basic rule is called the same origin policy, and it's been a cornerstone of web security for a very long time.
So, what do we mean by an origin? It's actually pretty simple. It's just a combination of three parts of a web address. The scheme, which is like HTTP or HTTPS, the domain, domain a.com, and the port number. If just one of those three things doesn't match between two addresses, the browser says, nope, you two are from different places.
What this means in practice is that a script running on, say, domain a.com can ask for anything else it wants from domain a.com. That's the same origin request. Totally fine. But the second that same script tries to fetch data from domain b.com, bam! The browser's security wall goes right up and blocks it. That right there is a cross-origin request.
And here's the big problem, right? That security wall is essential. We need it to stop bad guys from stealing our data. But the modern web we know and love is built on collaboration. We need our website to talk to Google's APIs, to grab fonts from Adobe, to pull data from all these different places. We need a safe way to poke a few very specific holes in that wall.
And that is exactly where CORS comes in. See, CORS isn't about tearing the wall down. It's about creating a really smart, secure passport control system. It's how a server can say to a browser, hey, I see that request from that other domain. I know them. They're cool. You can let them through.
The official definition here is perfect. It's a mechanism based on HTTP headers. These are just tiny little bits of text that get sent along with every web request and response. And it's in these headers that a server can give permission for a browser to access its stuff even if the request came from somewhere else. So let's see how this passport check actually works.
All right, so the most basic kind of CORS check is for something called a simple request. You can think of this like visa-free travel. If your request is really basic and is considered very low risk, the process is pretty streamlined. But as you're about to see, the web has a very strict definition of what simple means. It's kind of funny just how specific these rules are. To be considered simple, you can only use a get, head, or post method. You can only use a handful of standard, boring headers, and if you're sending any data, the content type has to be one of just 3 old-school formats. If you step outside of any of these tiny little boxes, your request is not simple anymore.
So for a simple request, it's a one-trip deal. Your browser sends the request, and it automatically attaches an origin header. This is like it's showing its passport. The server on the other end looks at that passport, and if it trusts that origin, it sends a response back with an access control allow origin header. That's the official entry stamp. Once the browser sees that stamp, it lets the data through to your script. Simple as that.
Okay, that works for the basics, but let's be real. Modern apps are way more complex. What happens if you need to send nicely formatted JSON data? Or what if you need to use a custom authentication header? These are considered more risky, and they require an extra layer of security.
And this is where we meet the pre-flight request. It's a brilliant idea. Before the browser sends the actual complex request, it first sends a little probe to check if it's okay.
It's like calling customs before you ship an expensive package to ask, hey, I'm about to send this thing. It has these specific characteristics. Are you going to let it through the border?
This little probe uses a special, super lightweight HTTP method called options. Now, this options request doesn't contain any of your actual data. It's just a quick ask. It says to the server, hey, would you allow it if I were to send a post request with, for example, a custom authorization header?
So it becomes this little two-step dance. First, the browser sends the pre-flight options request to ask permission. If the server's cool with it, it responds with headers that say exactly which methods and headers are allowed. Only after getting that green light, after getting that permission slip, does the browser finally send the actual request with all your data. It's a really smart way to make sure potentially unsafe requests are never even sent without approval.
Now, you might be thinking, hold on, making 2 requests for every single action? That sounds really slow and inefficient. And you'd be totally right. It would be. That's why the server can include another header, access control max age. This tells the browser, hey, you can remember these permissions for a while. In this case, for up to 24 hours, or 86,400 seconds, so it doesn't have to keep asking over and over again.
We're almost there, but we have to cover one last absolutely critical rule. And this one is arguably the most important of all, because it deals with our most sensitive information. So what about requests that send credentials? You know, things like cookies that keep you logged in, or authentication tokens that prove who you are. By default, for your own safety, browsers will not send these things on cross-origin requests. To make them go, you have to explicitly ask for it, which signals that this is a high-trust situation. And when you do that, the server has to play by an even stricter rule. Here it is, the big one. And it's so important I'm going to read it word for word. When responding to a credentialed request, the server must specify an origin, instead of specifying the asterisk wildcard. The asterisk, the star, means allow anyone. And think about that for a second. Would you want your login cookies to be sent to any website on the internet that asks for them? No way. The server has to name the one specific origin it trusts. So let's make this crystal clear. If your code tries to send a cookie, but the server just gives a lazy reply like, sure, anyone can access this using that star wildcard, the browser will block it, flat out. It refuses to expose sensitive data with such a generic permission slip. For the request to work, the server must respond by naming your specific origin, like https:/domain-a.com. It's like a personalized invitation, proving it's a trusted exchange. So let's bring it all the way back to the beginning. That cross-origin request blocked message you see in your console, it's not an error. It's not a bug you need to hack around. It's a sign that the web's security guard is doing its job. CORS is the sophisticated, careful negotiation that allows our rich, interconnected web to even exist, balancing that constant need to share with the absolute need to be secure.
And that leaves us with one final thought to chew on. CORS is a pretty brilliant solution for the web we have today. But as our digital world gets more and more connected, as data starts to flow in even more complex ways, it really makes you wonder, right? How will security models like CORS have to change and evolve to protect the web of tomorrow?